welcome to the third part of gas stoichiometry problem. Now, please note that before you proceed to watching this video, I hope you've already watched gas stoichiometry parts 1 and 2 to further understand the roadmap and the ideal gas equation. Now, looking at the stoichiometry roadmap, remember that when you're asked for volume or other physical quantities that relate to gaseous substances, that means you are dealing with gas stoichiometry. When we talk about gas stoichiometry, there's nothing new about the stoichiometry roadmap. It's just mole to mole using the mole ratio, and then you can extend from mole to mass or mole to mass of the given and the required. However, gas laws, just like the ideal gas law and the 22.4 liters, if it's at STP, these are extensions on the mole part usually, either the given or the required. Now take note, if it's gas law problem, it will be obvious because you will be dealing with terms like STP, or in the ideal gas law, you'll be given pressure, volume, or temperature, and then you'll be asked for any of that variable. So that's your hint that you're dealing with gas stoichiometry. It is also possible that you'll be dealing with limiting and excess reactant if you are having gas law extensions. That means it's just the same way as you do limiting and ER calculations. It's just that you need to extend it further using the ideal gas law or the STP conversion factor of any gas in which you have 1 mole is to 22.4 liters. Now let's apply it to the second problem here about the decomposition of potassium chlorate. It says here that what volume of oxygen gas at STP is produced in the decomposition reaction of 25 grams of potassium chlorate as shown in the reaction here. You notice that in the given equation, the potassium chlorate decomposition is already balanced, so we don't have to worry about that. Now, it says that it is at STP, so it's better that we put all the given variables so that it will be clear to us. We're given STP and 25 grams of potassium chlorate, and then you are asked for the volume of your oxygen gas. So, let's start. So, we're given STP in which the temperature, let me do that again, in which the temperature is 0 degrees Celsius, or in Kelvin, it should be in Kelvin, 273 Kelvin. That standard pressure is always 1 atmosphere. Then, of course, it's better that you put the R so you won't forget. The gas constant is 0.0821 liter dash atmosphere per mole Kelvin. Then another thing is we're given the 25 grams. The 25 grams is potassium chlorate, so that's mass of potassium chlorate. So let's see, that's 25.0 grams of KClO3. However, you're being asked for the volume, it's oxygen gas, and the oxygen gas is the one at STP. So that means these three things here are for O2 gas, not potassium chlorate. And potassium chlorate is not about oxygen gas. They're different. It's not a gas even. So what we need to do is, for this 25 grams of potassium chlorate, we can convert it to moles O2 because that's what we need also to calculate for the volume. Now, you have to get the volume of O2 gas, the V, which is the required. And you know that because this is at STP, you have an idea that 22.4 liters is to 1 mole of any ideal gas at STP can be used. So we can use that. But before that, we need to get the mole first of O2 from your grams KClO3. So this KClO3 has to be converted to moles of O2. So that's where the stoichiometry is, the conversion of the mass of potassium chlorate to your moles of O2. So because this is mass, potassium chlorate, that means it's a mass to mass conversion. So we start with a molar mass of potassium chlorate, which is 1K, 1Cl3 oxygen. So you get around 122.55 grams of KClO3 for every 1 mole of KClO3. KClO3. Okay. Next to that, after molar mass of KClO3, we're ready to shift from KClO3 to O2, in which from the balanced chemical equation, it's 2 is to 3. So the 2 has to be here, so we can cancel out KClO3. So 2 moles KClO3 for every 3 moles of O2. And since we're gonna look for moles O2, this is enough already. So that means putting everything in the calculator, the numerator together, denominator together, we will get 0.31 moles of O2. So that means our given are already complete. We already have temperature. So let's see. We already have temperature of O2, pressure, of course the R, and then the N value. So we can get our V. We have two options. We can use this at first, so which I'm going to show you now. Let's show that we can use our 22.4 because it's at STP, so we can use our 22.4. So we may begin always with the mole of O2. So we have 0.31 mole of O2 times the conversion factor at STP is 1 mole of any gas, in this case it's O2, occupies a volume of 22.4 liters. So in this case, putting this in the calculator, you will get 6.94 liters of O2. So this is the first one answer that you can get directly from this conversion because it is at STP. Okay? You see, it's an extension, so that means we do that last after doing the stoichiometry calculation. Or the other option is we can use the ideal gas law. Just in case you forgot this conversion factor, we can use the ideal gas law, in which it's just easy. We can just use the PV is equal to nRT in this case to get V that is over P. So cancel that out. So that's going to be V is equal to, we substitute N is 0.31 mole, and then we know the R to be 0.0821 liter dash atmosphere per mole Kelvin. Then times temperature from the given, it's 0 degrees, or it should be in Kelvin, 273 Kelvin, divided by our pressure, which is 1 atmosphere. Before you input this in the calculator, let's see if we can cancel out the units. Let's cancel out the units. Mole is below here, so you can cancel out the mole on top. Kelvin is also above here, and it's below here in the gas constant, so that cancels out, and atmosphere gets cancelled out, top and bottom. So we're left with liter. It makes sense. We should get a liter because we're looking for volume. So now we're ready to input all of this in the calculator, in which you get 0.31 times your gas constant of 0.0821 times 273 Kelvin. You get around 6.86 liters of O2. Now you see, the answers have a little difference between this and that. But nevertheless, both solutions are correct. It's just that for the STP direct conversion, the 22.4 is kind of rounded off. So that's why it's kind of far from your ideal gas law answer. But nevertheless, both approaches are correct. So again, if your stoichiometry problem is at STP, you may use this direct conversion right away, or you may just use your ideal gas law, granting that the basic here is you need to be able to get your N or moles of O2 from the given mass of potassium chlorate, because the calculation involves gases, not the potassium chlorate. So that's where stoichiometry is. So that's for the second part or the third part of your gas stoichiometry problem. I hope that you can follow through and take note that we just followed this roadmap of the gas stoichiometry roadmap, and it's always that same with density. Gas laws are just extension of your moles. Okay, so this has been Madam Narca saying don't stop learning, relearning, and unlearning. And please don't give up on this. Don't give up on whatever you're doing, because at the end, you will harvest what you deserve. You can harvest. Thank you so